Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss work. Work is basically a concept in physics. The idea of work is that if a given force causes a certain displacement, then the force times the displacement is the work done by the force. But in real applications, the force will vary from point to point during the movement of an object, and so consequently we have to use an integration to calculate work. Let's look at the formula. The work done by a variable force, capital F of x, directed along the x-axis from x equal a to x equal b is denoted as capital W equals the definite integral from a to b of f of x dx. Notice what we can do is think of the position of whatever's being moved as being x, and so the force at that location is capital F of x, and so thinking of it as being approximately constant with that value during the move from x to x plus dx, then the amount of work done to make this tiny displacement of amount dx is simply force times displacement f of x dx. And so consequently the total work is the integral from a to b, starting point to ending point, of f of x dx. When we're dealing with problems in physics, we have to keep in mind actual units, unlike mathematical problems where sometimes units are not really appearing. In any case, for work, the unit in the standard metric system is called the joule. That is, when a force of 1 Newton moves an object through 1 meter, then the work done is called the joule. It's 1 joule. In the case of the English system, we use feet and pounds. The force is measured in pounds, the displacement in feet, and so then the standard unit of work is called the foot-pound. So if your distance, for instance, is in inches, then you need to convert to feet in order to get to foot-pounds. So keep that in mind. We have to make actual conversions of units to put things in standard form. Now let's look at a problem stretching a rubber band. Of course, you know that when you stretch a rubber band, you have to pull on it with some force. A force of 2 newtons will stretch a rubber band 2 centimeters. Now remember, we have to deal with meters, so 2 centimeters is 0.02 meters, since a centimeter is 1/100th of a meter. Assuming that Hooke's law applies, how far will a 4 Newton force stretch the rubber band? How much work does it take to stretch the rubber band this far? Well, remember, Hooke's law is a very simple law. It just says the force to displace the object by an amount x is a constant k times the displacement. Hooke's law applies to things like springs and rubber bands, anything that can stretch. It's really an idealized law, and so you need to keep in mind that it really only applies in practice, in real practical situations, for small displacements. For instance, if you stretch the rubber band too far, it's going to snap, and that clearly means Hooke's law is broken down. But in any case, that's Hooke's law. Now, when we use this, we'll just drop the x, the parenthesis x after the f, and it'll be simplest to write it as simply Hooke's law, F equal kx. So the information in our problem is that a 2 Newton force displaces 0.02 meters. And so consequently, we can say 2 newtons equals k times 0.02 meters when we substitute in this formula the 2 newtons for F and the 0.02 meters for x. And so now we can calculate k very easily. You see, we just solved this equation for k, and I'm going to keep the units in there. So k is 2 newtons divided by 0.02 meters, which I'm using just m for meters here now, which is very common notation. And notice 0.02 is really 2 divided by 100. So what we have here is 2 divided by 2 over 100. And now we have newtons over meters. And so you see the units of our constant for the rubber band is newtons per meter. The 2's cancel, the 100 comes up top, and so we see our constant for the rubber band is 100 newtons per meter. Okay, now a 2 Newton force displaces by 0.02 meters. It should be pretty obvious that a 4 Newton force being double the 2 Newton force is going to double the displacement, because this is saying force is proportional to displacement. If I put this actually into the formula, 4 newtons equals kx, well, k is 100 newtons per meter, so this would say x is 4 newtons over k. And so when we replace the k by the 100 newtons per meter, notice we simply get 0.04 meters. So there's our displacement that the 4 Newton force is going to cause. But notice that if we take the rubber band and pull it out 0.04 meters, the amount of force we're applying at each position along that displacement varies from point to point according to the formula F equals kx. So to compute the work done, we're actually going to have to integrate the force from 0 displacement up to 0.04. That is, the work done is the definite integral from 0 to 0.04 of f dx, and f is kx. So that's the definite integral from 0 to 0.04 of kx, and remember k is 100 newtons per meter, so we just substitute in. We have 100 definite integral from 0 to 0.04 of x dx. We've taken the constant out, and the antiderivative of x, of course, is x squared over 2. So we have 100 times x squared over 2 evaluated from 0 to 0.04. So clearly putting 0 in contributes nothing, and so our final answer for the work is going to be 100 times, well, let's divide the 2, times the 0.04 squared, which I'll write as 4/100ths squared. Now notice here 100 squared cancels with 100, leaving 100 down in the denominator. 4 squared is 16, divided by 2 is 8. So we get 8 divided by 100. And remember, we've used meters for displacement now, and newtons for force, and so consequently our unit of work is joules. We have 8/100ths, or 0.08 joules. Okay, let's look at a problem where we're going to be using the English units, and we're going to be discussing the problem of lifting an elevator and how much work is done just to lift the cable itself that holds the elevator. Lifting an elevator cable. An electric elevator with a motor at the top has a multi-strand cable weighing 4.5 pounds per foot. When the car is at the first floor, 180 feet of cable are paid out, and effectively 0 feet are out when the car is at the top floor. How much work does the motor do just lifting the cable when it takes the car from the first floor to the top? Notice that as far as the work that the motor does lifting the elevator, that would simply be the weight of the elevator, which is the force of gravity on the elevator, which the motor has to counteract. So the motor has to lift, just to lift the elevator, is constant, equal to the weight of the elevator in pounds, and that would just be that weight times 180 feet. But as far as the cable is concerned, as the cable is taken up, the cable gets shorter, and so the full length of cable at any height is less than at the start, and so we've got a variable force because of the cable. So in effect, the total work would be the work lifting the cable plus the work lifting the elevator. Well, let's look at a picture here. Here's the motor, and I draw a little schematic here. Think of a pulley that is operated by the motor, and here's the cable, and here's the elevator, and so the motor pulls the cable up, winding on the pulley. Now, when the elevator's roof, the top of the elevator, is at height y, at distance y from its position at the first floor, then the amount of cable out is 180 minus y. Of course, the total distance from the top of the elevator when it's at the first floor position all the way to the top of the pulley is 180 feet. And so what we need to do, in effect, is calculate how much work the motor does when it moves the elevator up just a little tiny bit. Let's think of it as moving it up an amount dy. And consequently, during that little move, we can think of the amount of cable out as being constant with value 180 minus y. That's the number of feet of cable out when the elevator is at height y. And so now we can use the fact that the cable weight is 4.5 pounds per foot and calculate dW, the work to raise the bit of cable from the original height y to the top. dy equals the length of the bit. dW is then, well, it moves 180 minus y feet. The bit that it wraps up in moving dy is then a displacement dy. The weight is 4.5 times the length of cable times the displacement dy, and that's the amount of work that's done to raise that stretch of cable that's effectively 180 minus y feet just by that little displacement. And so consequently, y goes from 0 all the way up to 180, and so that gives us our work integral. W is the definite integral from 0 to 180 of 4.5 times the quantity 180 minus y dy. And so that's all we have to work out in order to calculate the work. Okay, so here we want to anti-differentiate. Of course, the 4.5 comes out since it's just a constant. Antiderivative of 180 with respect to y is 180 y, minus the antiderivative of y, which is y squared divided by 2, and this is to be evaluated between the limits 0 and 180. So we get 4.5 times, when I substitute 180 in for y here, I get 180 times 180, or 180 squared, minus 180 squared over 2. Well, 180 squared minus a half of 180 squared is simply a half of 180 squared. So we get 4.5 times 180 squared divided by 2 for the work. And doing a little cancellation here and multiplying out, we find very easily that is 72,900. And what are our units? Well, remember, here we're measuring displacement in feet and force in pounds. Remember, the cable weighed 4.5 pounds per foot. So here our units are foot-pounds. Okay, many problems involving work are problems involving pumping out certain liquids out of tanks. Let's look at one. Emptying a tank. A vertical right circular cylindrical tank measures 30 feet high and 20 feet in diameter. It is full of kerosene, weighing 51.2 pounds per cubic foot. How much work does it take to pump the kerosene to the level of the top of the tank? So let's look at a picture. Here I've drawn a circular cylinder. Think of that as our tank. There's our tank. The top of the cylinder, the whole thing, in effect, is circular in shape, so its diameter is 20 feet across, which, remember, that means its radius is 10 feet. Now, notice that in pumping out the cylinder, what I can think of, the cylindrical tank, what I can think of is that amounts to taking each little horizontal slab of kerosene and lifting that to the top of the tank. And so if I'm considering a slab of kerosene here that's at height y, since the whole tank is 30 feet high, to move that slab to the top, it has to move a distance of 30 minus y. What is the actual volume of such a slab if its thickness is simply dy here? Well, notice the volume would be the thickness multiplied by the area of the slab, and the area is pi times 10 squared, since that is a circle of radius 10. So pi times 10 squared dy is in effect the volume of that slab of kerosene that has to be moved from height y all the way to the top. How far does it have to go? It has to go 30 minus y feet, and of course, what's the weight? Well, the weight is the 51.2 pounds per cubic foot multiplied by the number of cubic feet for the slab. And so, in effect, this weight of the slab multiplied by the distance it travels to get to the top is the bit of work dW that we do in raising that slab. And of course, emptying the full tank means raising all of those slabs, so we have to integrate this expression all the way from 0 up to 30 feet. So consequently, the integral we have to work out is W equals the definite integral from 0 to 30, pi times 10 squared, 51.2 times the quantity 30 minus y dy. And so notice all these are just constants, and we can pull them out. 10 squared is 100. We have 51.2 times 100 times pi times the antiderivative of 30 minus y here. Antiderivative of 30 with respect to y is 30y, minus antiderivative of y itself is y squared over 2, and that's evaluated from 0 to 30. So we get 51.2 times 100 times pi, and let's put in the upper limit, y equals 30. The first term gives us 30 times 30, or 30 squared, minus 30 squared over 2. Well, 30 squared minus a half of 30 squared is simply a half of 30 squared, so we get 51.2 times 100 times 30 squared divided by 2. And of course, when we multiply all this out, what we find is, oh, we can't forget this factor of pi. What we find is we'll get 2,304,000 pi, and what are our units? Foot-pounds. Remember, our kerosene weight is given to us in pounds per cubic foot, in effect its density, and so weight is in pounds and our distance is in feet, so our unit of work is going to be foot-pounds here. Well, physicists have found that there are several concepts that help with understanding motion and simplifying calculations: force, momentum, and kinetic energy. Let's see how kinetic energy relates to Newton's laws. Kinetic energy. If a variable force of magnitude f of x moves a body of mass m along the x-axis from x1 to x2, the body's velocity v can be written as dx dt, where t represents time. In effect, what we're doing, in a sense, is taking time as a parameter for the motion. So consequently, we can use Newton's second law of motion, which says force equals mass times dv dt, where v is velocity, so notice dv dt is acceleration. Force equals mass times acceleration. And the chain rule, which says dv dt equals dv dx times dx dt, and of course notice dx dt is velocity, so we have dv dx times velocity, or v dv dx. So we use that to show that the net work done by the force in moving the body from x1 to x2 is W, of course, by definition, equal to the definite integral from x1 to x2 of f of x dx equals 1/2 mv2 square minus 1/2 mv1 square, where v1 and v2 are the body's velocities at x1 and x2. Now, keep in mind that this quantity, 1/2 mass times velocity squared, is what in physics is called kinetic energy. So in physics, the quantity 1/2 mv squared is called the kinetic energy of an object. So let's look at this. In physics, the expression 1/2 mv squared is called the kinetic energy of a body of mass m moving with velocity v. Therefore, the work done by the force equals the change in the body's kinetic energy, and we can find the work by calculating this change. That is, remember, we have W equals the definite integral from x1 to x2 of f of x dx equals 1/2 mv2 squared minus 1/2 mv1 squared. And so consequently, the work done is the change in the quantity 1/2 mv squared, the change in the kinetic energy. Okay, let's see why that is true. First off, let's consider the concept of momentum. The momentum P is by definition mass times velocity. And Newton's second law of motion technically says that the force is always the rate of change of momentum, so it's the rate of change of mv. In the case where the mass m is constant, then the mass can be pulled out of this equation and it becomes m times dv dt. Of course, mv is momentum. Well, since momentum depends on velocity, obviously the standard symbol in physics for momentum is P. We could also write the kinetic energy in terms of momentum, and consequently what happens is that the law that the work is the change in kinetic energy is true even for variable mass. But in any case, let's just work out the case where m is constant. So in that case, what we're thinking now is time is a parameter. So work is the definite integral from x1 to x2 of f of x dx, and we're going to, in effect, make the substitution x equal x of t, and so that means dx is dx dt dt, which dx dt is v. So with that substitution, dx right here becomes v dt, and here we have work is then the definite integral from time t1 to time t2, that would be our limits in terms of time, of f at x of t, v of t dt. Now here's where we're going to use Newton's law. This quantity right here now is m dv dt. So let's put that into the equation. Making that replacement, our integral becomes w equals the definite integral from t1 to t2 m dv dt times v of t dt. Well, now let's make a substitution again. We'll substitute u for the function v of t, because our integrand, in effect, is a function of v times the derivative of v. See, so it's a candidate for substitution. When we do that, du is dv dt dt. And so du being dv dt dt, this quantity dv dt times dt, notice the dt's canceled, that's just dv. In effect, u equals v. So let's actually work out that. So notice what we get. W is the integral now from v1 to v2, because we've substituted, in effect, v for v of t, mv dv dt. I'll leave the dt's in a moment, so we cancel them, you see, and so we just have mv dv from v at time t1 to v at time t2. Well, now notice what we get is the m is a constant. We're assuming that we can take it out. We have the definite integral from v1 to v2 of v dv. And so that is v squared over 2, the antiderivative of v with respect to v. And so we get mv squared over 2 evaluated between the limits v at time 1, which we'll call v1, and v at time 2, which we'll call v2. And so that is 1/2 mv2 squared minus 1/2 mv1 squared. And so consequently, we see our work is finally the change in kinetic energy. Well, this is very convenient formula in many situations. For instance, if I know the work done and I know the velocity at the initial time, I can calculate using this formula what the velocity at the final time is, just knowing the mass. Or conversely, if I know the velocities at the start and at the end, I can use this change to calculate the work done. A good example of the usefulness of the concept of kinetic energy is in the problem of calculating the work done to throw an object to cause it to move with a certain velocity. For instance, consider what happens when a softball pitcher throws a softball. The motion of the softball pitcher's arm is very complex, and so to actually calculate the work done from the time he starts moving the ball till the time he releases the ball would be an extremely complex integral to calculate. On the other hand, one thing we know is before he throws the ball, its velocity is 0, and if we measure the velocity at which he releases the ball, then the change in kinetic energy totally measures the amount of work he did, however he did it, of course neglecting the work against friction. Let's look at an example. Softball. How much work has to be performed on a 6.5-ounce softball to pitch at 132 feet per second, of course, which is 90 miles per hour? Well, let's look at the basic facts in this problem. We want to calculate the work to pitch a 6.5-ounce ball 90 miles per hour. So keep in mind the conversions. There's 16 ounces per 1 pound in weight measure, and a simple way to convert from feet per second to miles per hour is to use the conversion 88 feet per second equals 60 miles an hour. That's exact, and that's a very useful relationship to remember when dealing with physical problems. So why don't you try this one on your own and see how I work it? Keep in mind the concept of kinetic energy is going to simplify the calculation. Okay, let's look at the basic facts then. 60 miles per hour is 88 feet per second, so obviously 30 miles per hour is 44 feet per second, and therefore 90 miles per hour being 60 plus 30 is the sum of 88 and 44 in feet per second, and if I add these two, you easily see it's 132 feet per second. Now, the ball starts with velocity 0, and so the work done is simply the final kinetic energy of the ball, which is 1/2 mv squared. How do we calculate the mass? Well, there are a couple of considerations here that you have to keep in mind. The weight of the ball is 6.5 ounces, and there's 16 ounces in a pound, so 6.5 divided by 16 is the weight of the ball. Remember, weight is the force of gravity on the ball, and the force of gravity is effectively 32 feet per second squared per pound. Under the Newton's law, force is mass times acceleration. That means to convert from weight back to mass, we have to divide by the acceleration of gravity. So that's one thing that you have to keep in mind when dealing with the English system of units. and that is when weight is given to you in pounds. You have to convert to mass. In some problems, that means you're going to be dividing by the acceleration of gravity, which is 32 feet per second squared. So to summarize then, the ball weighs 6.5 divided by 16 pounds. Weight equals the force of gravity, which is mass times the acceleration of gravity, and therefore the mass of the ball is the 6.5 over 16 times 32. So how do we calculate the work? We use this mass times a half v squared, remember, because work is equal to the final kinetic energy in this case. And so what we get is the work W is 1/2 6.5 divided by 16 times 32 times the quantity 132 squared. Remember, that's the velocity, final velocity in feet per second. So we're keeping our distance units in feet, and our mass has been converted to, in effect, pounds divided by acceleration of gravity. So that means, in effect, what we're going to get in the end here is the work in foot-pounds. So calculating this, we finally end up with 110.601562, and this would be foot-pounds. Well, we've done several calculations of work. Remember, work is defined as the definite integral of force against displacement from beginning position to end position. Also, keep in mind the concept of kinetic energy can be very useful in simplifying work calculations, since the amount of work you do on a body will simply be equal to the change in the kinetic energy, and the formula for kinetic energy being 1/2 mv squared is easy to calculate if you know the mass and velocity.